Well, good day. Today I'm going to talk about kind of a case study of something that I've been working on for about a year and a half. Crunchy's been working on. Basically creating a containerized environment around the Postgres database. And Crunchy Data, a little bit about us. We're a Postgres company based in the US. It's what we work on. It's our niche. It's really our focus. We offer secure support. There's several committers and various Postgres folks in the community work for us. So it's really what we do. And so for me, my opportunity with them was to figure out a way to containerize Postgres and make that experience good for people that want to deploy Postgres in kind of a cloud environment. Crunchy offers up a certified version of Postgres, which is the open source bits, basically in a packaged format. And that's something that we offer to customers. It's passed common criteria certification, which may mean something to some of y'all that work in DoD or federal space. So why would you containerize Postgres? What are some of the things? Why would you do this? One is to encapsulate any complexities around deploying a database. Installation, configuration of a database can oftentimes be something that's complicated, at least for a lot of developers. In places I've worked anyway, usually you go to a database group, they would provision you a database, and kind of the end consumers that developers really didn't know the complexities of that. So this is really a way to give developers in particular a quick way to spin up a Postgres database and not have to worry about all the permutations and complexities that may be involved with that. The other is, whenever we started doing this container, originally I started with the Postgres container, and that was great. And then it quickly became obvious that there was a need for other containers. Things like being able to do a database backup, things like administering or monitoring containers of Postgres that you might have deployed. So containers provide a relatively lightweight way to spin up or deploy Postgres. And for some environments and some customers, being able to maybe spin up 50 databases really rapidly is what their business requires them. And before, that used to be a very timely or costly experience. So containers really enable that rapid deployment. And most customers we're dealing with now are putting their applications in more of a cloud environment as well. So we wanted the database to go along with, say, web applications or end-user applications. So we want that same kind of lightweightness and rapid deployment model for databases as we did for web applications. We use Docker for this. About 2.5 years ago, I was working with running Postgres and Openshift whenever it was pre-Docker. And then when Red Hat announced they were going to do Docker, I was kind of the guy standing there going, what's Docker? And we kind of made our bet that was going to be the widely adopted container platform. And I think so far that's turned out very well. So what are some of the design goals of a Postgres container suite? Early on, I wanted to design the Docker files in such a way that I could support different types of operating systems as the base image. And I wanted to provide this container suite on a consistent base image. Customers that we deal with, they would prefer to manage and deploy usually one kind of operating system. So that applies with their containers as well. So all of the Docker files in Crunchy Container Suite are either based on CentOS 7 or RHEL 7, and that was by design so that whenever you deploy the container suite, you're able to deal with one consistent base image and deal with security issues and whatever with that one base image. It may support other ones in the future, but those are the ones that we initially targeted. The other is we wanted to support different deployment models. So the container suite early on was designed to deploy on just pure Docker, then on Openshift, and then as well on Kubernetes. And recently I've started on a version that will work on Mesos Marathon. So that is really, I guess, the power of Docker being a standardized container suite is I'm able to, just through configuration files, target these different orchestration environments pretty easily and in a pretty seamless way. The GitHub project that I'll have a link to in a second has examples for all of those environments, deploying the container suite in all of those different environments. And there will be probably others added to that list as I learn more about some real exciting new container platform, orchestration platforms that will certainly grow over time. All of these basically containers, Postgres containers in particular, all have to address the issue of persistence though. So people ask me all the time about Postgres data and where's it stored. Well, all of the data is offloaded onto outside of the container, obviously. So you get to the data files for Postgres through some kind of volume mount. And all of those different deployment platforms give you different options for persistence and how you mount volumes and how you provision volumes. I could probably talk for 2 hours just alone on all of the various ways and gotchas and security issues. So that's a big topic just unto itself. One of the goals, or design goals with this, was to allow end users to customize Postgres configuration. You can configure Postgres in like an infinite number of ways, it seems like. So things like the SQL that initializes a database, for instance, is something I wanted to be outside or mounted outside of the container itself. So that enables users to customize the objects that populate the database when it comes up. Things like the Postgres HBA conf and PostgreSQL.conf files are other examples of, you can use the ones that are generated or initialized by Postgres by the container itself, or you can mount those externally if you want to completely control those configuration files. There's other examples too where maybe you don't want to supply your own configuration files, but maybe you want to tweak just some values inside a standard configuration file. So those examples are those kind of things are exposed with environment variables. And then lastly, with this being open source as well, you can pull down the Docker files and completely customize the behavior as you want. So all of those things were design goals really early on. And the goal was to make this container suite, as usable and as extensible by as many wide of audience as we could make it. Really, any database as a service type container environment, you would want those kind of extensibility features in it. And you'd want to look at those from kind of the beginning if you were going to look at, non-Postgres database container environments or container suites as well. You want those kinds of extension points. Postgres in particular, some of the things that customers ask us is they wanted the ability to create a Postgres streaming replication type cluster environment. They wanted to do that pretty easily. And the reason is that was something that a lot of them had struggled with and doing it in a consistent way. And some shops found that kind of complicated. So clustering Postgres was an early design goal as well. Replication is part of that, and we wanted to support either synchronous or asynchronous replicas. So Postgres is a single master database today, and then you can have multiple read-only replicas. So that's another design constraint whenever you talk about building a container suite, is you have to keep that in mind of the inherent way Postgres replication works. Multiple locale support is something that's built into the container suite for the Postgres database container. And then in a Kube environment or an Openshift environment, we support the ability to encode your database credentials in secrets. And that's a feature that's just unique to the Kubernetes environment. Again, I talked about the ability to override config files. And then the ability to use a random UID instead of a normal Postgres UID was something that I had to basically learn. And that's in particular comes into play in an Openshift environment like Openshift Dedicated, where that's another targeted environment that with a little bit of configuration, I was able to make Postgres basically work with a randomly assigned UID, and that's unique to the Openshift PaaS environment. That took a while to figure out as well. It wasn't something I'd ever done before, but that's an example of a little bit of wrapper code inside the Postgres container enabled you to do something like random UID support. Features like restoring a database from a backup or other design features, which came immediately after the initial database container. It was like, okay, great, I've got a database container, but I would really like to be able to run another container to perform a backup on it. So that gets you into kind of like more than just a database container. It started us thinking about a suite or kind of a database as a service, and what does that look like? Backup and restore is a big feature of that. And right today, the container suite supports a full database backup using a Postgres utility called PG-based backup. So from a design perspective, I didn't want to recreate PG-based backup. It comes with Postgres. So the way in which the philosophy with this container suite is when there's a Postgres utility that really works and is standardized within the community, we just want to enable that use or execution of that in a container environment. So we created a backup container, which is called Crunchy Backup. And when you run that container as like a Kubernetes job, you just pass it enough information about a running database container, and it begins to create a full database backup. It'll persist it off to something like an NFS volume mount, and all of those NFS volumes are basically time-snapped, or so that you can then fire up a brand new database container, pass it in an environment variable where its backup is, and it will restore from that backup. That is a very, very small, thin container, but it's an example of not reinventing the wheel, but just cloud enabling a already bulletproof Postgres feature or utility. Typically, kind of to backtrack a little bit, typically that container, most of the logic in it is just a simple bash script as well. So it's very easy for people that if you understand bash and a little bit of Linux, you can get in and look at the Docker file and tweak that Docker file and the bash script that just merely wraps PG-based backup and customize it to fit your needs. So that was the other goal, was to kind of keep the orchestration inside the containers to a bare minimum and then depend on orchestration outside of the containers. So I've seen some people, they'll write a container, they'll bake into it a million different things, even orchestration logic. And I've really tried to resist that temptation and make this just a real lightweight set of Docker or wrappers essentially around some of these things. High availability was another thing that came up, as most database as a service environments have some mechanism of connection pooling, of handling automated failover. So there's a container called Crunchy Watch that does nothing but looks at a Postgres master container to see if it's responding. If so, great, but if not, it will trigger a failover to one of those slave replicas. Again, a very small amount of code. That's probably about like 100 lines of bash script. It leverages a existing Postgres utility called PG is ready. Again, that was really the philosophy, and that's the way we like to build out this container suite where possible. Database monitoring was a little bit different. I saw an opportunity to take something like Prometheus and make use of it and store Postgres metrics. There's different kinds of metrics tools out there, and this was an attempt to say, what can I leverage out there in the open source space to create a cloud-based Postgres monitoring metric tool? And what I ended up with was Prometheus as the data store, and I used the Prometheus push gateway as a means to kind of temporarily hold metrics. And then I wrote another container called Crunchy Collect. And Crunchy Collect is a small amount of Golang code that talks to a database container and basically pulls 20 or 30 different Postgres-specific metrics from the container using a SQL interface to the database, and then also externally, because if you place that Crunchy Collect in, let's say, a Kubernetes pod, it has access to the data files. And so it can do actually metrics-based work against the data files of Postgres as well. It collects those and pushes them off to Prometheus. And then I use something like Grafana. Again, all very, very well-known, stable, open source projects, containerize those, and now I've basically got a custom Postgres metrics collection and graphing dashboard with, again, very little bit of code. And I think that's really the future. Again, a nice aspect of using open source projects. Things like backups and running database vacuums. People were asking me, well, that's pretty neat, but my administrators, I need to run these jobs on a periodic basis. And my administrators won't give me access to like the cron system. How can we do that with containers? So I found a great open source project that's a very small cron implementation in Golang again. Wrote a container called Crunchy DBA and wrote a little bit of glue code in there so that it will spawn off, based on that cron schedule, backup containers and then also vacuum analyzed containers. And that gives your normal user of this suite the ability to automate basically different DBA tasks. And over time, I see that growing out into a much richer capability to do, say, reporting and also health check and things that a DBA would do, just routine tasks. But this moves the responsibility of automating all that. Now it gives the keys kind of to a developer. If they can run the Crunchy DBA container, you basically now have the ability to have your own schedule of things that you want to do. There is a one-to-one relationship between the Crunchy DBA container instance and a database container as well. So that was kind of the model there, is if you had 50 databases, you could assign a unique DBA container to each one. So it's kind of a virtualized DBA that you would have associate. So again, I was trying to cloud scale out automation or admin task and monitoring along with the database container. So what did we end up with at the end of about a year of development? This is what we ended up with. So I've talked about most of these. There's Crunchy PG, which is just the database container. It runs Postgres 9.5 currently. That gets updated every time there's a new Postgres release. Crunchy Backup runs that PG-based backup. It's meant to be run like a Kubernetes job. So you run it once, it executes, and it dies. So it's not a long-running container at all. It starts, it finishes, it does its job, and that leverages features like the Kubernetes job construct. Crunchy PG Badger is an example of, again, taking an existing Postgres utility written in Perl, never designed with a web interface or with an HTTP interface or cloud in mind. Probably wrapped it with about 60 lines of Golang code to put an HTTP wrapper around PG Badger utility. And that way, if I add that container inside a Kubernetes pod, and it has access, therefore, to the Postgres data files, it can generate static log analysis off the Postgres logs. And hopefully I'll have time, I'll show you a demo of that. But again, very simple amount of code, but it enables you to kind of cloud enable something like PG Badger. Crunchy PG Pool is a very similar example. There's a product called PG Pool, an open source project, which is a smart Postgres knowledgeable load balancer that understands how to load balance between a master and multiple Postgres slaves. People use it as a single entry point into a Postgres cluster. Took that utility, wrapped it in a Docker container, add just a little bit of integration points so that it can understand what your master service and your replica services are, how to find them. And now whenever you stand that up in front of a Postgres container cluster, you essentially have a smart load balancer. Crunchy Watch is the automated failover container I mentioned. Crunchy Collect is really the entire suite of Crunchy Prometheus, Grafana, and the Prometheus gateway, all kind of just wrapped up under something we call Crunchy Collect. But there's also an actual Crunchy Collect container that is that Golang code that scrapes or pulls Postgres metrics. Crunchy DBA we mentioned, which is just a simple cron scheduler with a small amount of glue code that leverages another feature of Kubernetes called a service account. And service accounts enable you to do things like dynamically talk to the Kubernetes API and dynamically, therefore, spin up containers on demand. So that's how it's able to dynamically spawn off things like backup jobs and vacuum jobs. And then the last one that we created was a containerized version of another open source project called pgadmin 4, which is a brand new rewrite of the older pgadmin tool. pgadmin 4 is a web-based console for Postgres. So, and the build of it is kind of interesting if you try to build it from source. So this was a good example of when you containerize something like that, it becomes way more consumable for a suite of developers. And this is something that if you had 50 Postgres developers, or 50 developers in general, you could give them each the pgadmin 4, and they instantly can connect to databases and start using it and not have to worry about building pgadmin 4 themselves. Orchestration. Orchestration intersects with something like this container suite in a number of different ways. Replicas need to be able to look up their masters, and that ultimately usually turns into a DNS resolution. So when you run a container suite in all of these different orchestration environments, you need to think about, okay, how am I going to do resolution? In a pure Docker environment, you may do that just with container links. okay, if you're not running some kind of DNS service. But in something like Kubernetes or Openshift, you can leverage the DNS that's built in there. So that's how some service discovery, or the service discovery that we're making use of. Typically when a replica runs, it just needs to find its master, and it needs to be able to look that up in some way. So that's something orchestration frameworks make a lot easier for you than if you didn't use an orchestration framework or tried to roll your own. But that places a burden on you to understand DNS networking, make sure that your DNS environment is set up. And networking in general, multi-host Docker is where orchestration frameworks, I think, really shine and make your life easier. As somebody who early on tried to set up my own multi-host Docker environment 2 years ago, it was definitely a challenging thing. There's also another environment I didn't mention, but we've ported this to actually work with Portworx too. And Portworx was here yesterday demoing, and that's basically they offer a Docker volume driver mechanism. So there's also, if you look in the examples, a way of running the Crunchy container suite to use the Portworx environment. And that's a persistence mechanism just in a pure Docker environment that you can leverage to do replicated volume management. So that's an interesting one to look at if you've never looked at Portworx. Let's see, that's a swarm deployment. Nothing interesting there, really. You probably know Swarm. But when you talk about multi-host, you have these different deployment models depending on what orchestration engine you have, and different networking in particular, and different networking choices. Ultimately, though, in terms of the Postgres suite, really all you need is a way for replicas to look up their master, and for you to be able to access databases through things like host names or container names. And the examples that we have out there, you'll see how I do that. If you, there's a document for each environment that the container suite supports. Persistence in general is an interesting topic. I could give a separate discussion on that, but there are some interesting things with Postgres. You want to have a reliable write. So whatever file system you're writing to, if it's really low or really slow over a network, it's obviously going to impact your Postgres performance. So when you talk about deploying these containers for real in a production setting, the choice of your persistence is really key. And that's where the orchestration frameworks really, I think, differentiate themselves. And if you were going to deploy Postgres, for instance, especially clusters of Postgres, that would weigh probably into your decision on which orchestration framework. And also, once you pick an orchestration framework, usually they offer up multiple different choices for file systems. That's probably a separate discussion, but I would say that whenever customers try to deploy this always comes up, and it's always a big issue of, okay, which storage infrastructure should I use and why? And then how do you monitor and measure Postgres performance on that? Hopefully I'm going to give you a demo of this, but I cooked up an example called the Kitchensink Example. So what can you do with this other than just deploy a single database, which is sort of uninteresting? So I cooked up this example that tries to use as many of the containers as possible to deploy a non-trivial Postgres deployment. So what this has is a master pod. This is a Kubernetes example. The master pod has 3 containers in it. A Badger, which is going to give me log analysis reports. The master database itself, the metrics collector, which collects metrics. Then there's going to be a replica controller. And this basically lets me spin up a replica that's going to replicate from the master, But then also it's going to allow me in Kubernetes to scale that replica up dynamically. And that's, again, a feature of an orchestration engine that you want, is that ability to scale things up dynamically. I want a replica, though, that is also synchronous. So I'm going to spin up a synchronous replica. The other replicas are asynchronous. And I want a synchronous replica that's going to guarantee that my master is always in sync with something in case the master falls over. Then I'm going to put a master proxy in front of the master container, and then I'm going to use that as basically a router or a service endpoint into the master. I'm going to do the same for the replicas. The replicas that are pointed to both the synchronous and the asynchronous. So it's going to do round-robin load balancing between those. Then there's going to be the watcher that's going to look at the master and see if, let me go back, and see if the master falls over, and it'll perform a failover onto the synchronous replica pod. There's also some things there. The PG pool is deployed. That's going to, again, load balance between the master service and the replica service. So it's another layer of load balancing. So in Postgres, only a master can do writes. Replicas can only do reads. So PG pool is the only thing I've seen smart enough to direct SQL traffic to the right endpoint based on the type of SQL statement. So there's a service in front of PG pool as well. So that example ultimately is worked up into lots of different Kubernetes JSON templates. These are all out in the GitHub. And you execute, some people have never worked with Kubernetes, so I'll put this slide in here. But it shows you, you execute these commands, it reads in these templates, which acts as recipes for the build out of all of that infrastructure on that diagram. And this example's out there, it's called Kitchensink, you'll see it. Inside those JSON files, again, is kind of a recipe of exactly what container should it start up and what kind of parameters should it pass. That's the location of this example if you really want to see details of a real complicated example. That's just the dashboard for Kubernetes because there's nothing else graphical to see. And then just to summarize, the Crunchy Postgres Container Suite is just one example of a database as a service. There's lots of other ones out there that are being built or have already been built. But I think it is representative of what people would run into, the kinds of issues if they were going to build their own database as a service suite. Networking and storage are particularly hard to do when it comes to building out clustered databases, in particular storage and replicating storage and making sure that it meets your kind of SLAs. Monitoring administration need to really mirror the agility that you get whenever you deploy databases. If you deploy a database container in a second, you really don't want to go use some really slow process to deploy administration and monitoring features. So really what you want to do, I think, is try to automate the administrative and monitoring features along with the database itself. Using an open source database like Postgres made this a lot easier. I could take all of these utilities and code, build out these containers without worrying about a lot of closed source licensing issues, which would make this a lot harder to do. So I'm freely able to build out these containers and distribute them like I do. And in some cases, I even had to basically go into the Postgres C source code to figure out exactly what it was doing to make it actually work in things like Openshift dedicated. So if that had been closed source, that probably would have been hard to debug some of those issues. And then one size does not fit all. So really, it does place a premium on your configuration design. That's my contact information. If you've got any questions, there's also the GitHub site on here. You can download all of this and the containers themselves are out on Docker Hub. I don't have the Docker Hub link there, but it's, if you do a search for crunchy data on Docker Hub, you'll see all of the different containers. Now, if I've got 2 minutes, I'll just show you a brief demo. No, we're out of time. Okay. So anyway, thank you very much.